But the other major set that I was talking about is the algorithmic models, right? And so here, you guys probably have heard of k-nearest neighbors. It's basically, it's like an algorithm for peer pressure. You don't know who, what group you belong to, and you look at where you are, and you look at your closest neighbors, and you're like, oh, I'm probably part of the nerds. I definitely was classified as a nerd in high school. Or I'm part of the jocks, because these people are part of the sports team. That's what k-nearest neighbors does. Obviously, the distance metric you use, you could do Euclidean, Manhattan, Chebyshev, Minkowski. These are all different possible classifications. But for any point that's not classified, you just look at who's closest, and you take the k nearest neighbors and say, well, by some sort of majority vote, I'm going to classify you as such and such point. So you could do one nearest neighbor. You might get a plot like this. But it's really, really patchy and not super satisfying, really. I mean, you're seeing that in here, I'm going to classify any point that lands in here as belonging to the blue group, when in reality, everybody else around that whole area belongs to the orange group. So one nearest neighbor might be a little too small. You might look at 5 nearest neighbors, or they also have 15 nearest neighbors, and I hit the button. OK, there we go. 15 nearest neighbors. This one's probably a nice decision boundary. Obviously, you're going to have some sort of misclassifications in here, but it's not really the end of the world. And then here's how you run k nearest neighbors in R. And this is doing a little bit worse than the other two methods. But part of the reason for that is this is a large P data set. And for k nearest neighbors, the pros are that it's really intuitive. I mean, you can explain it. I mean, that's why it's been around for a while. It's just, well, let's see what other points are nearby, and that's going to give you the best classification. It's nonlinear. You don't have to draw a straight line. It could be real choppy and patchy. And it can be robust against noisy data if you choose a large K. So if you've got some noisy observations, you're going to say, maybe look at my 20 nearest neighbors and classify based on that. It helps with that. So it's most appropriate for when you've got a lot of observations and not a whole lot of predictors. Because what can happen is you have the curse of dimensionality, where if you've got a whole bunch of predictors that are not really helpful, when you're trying to calculate that distance in some sort of p-dimensional space, you're just going to get pulled all over the place. And so when you actually make some sort of classification, you're kind of in trouble. And there's large storage requirements computationally, because when you get a new observation, you have to plug it in, and then it has to search for its k nearest neighbors and make some sort of classification based on that. So it's not like you get some nice little model with some parameters and you just feed in a whole bunch of new observations and you get predictions. You have to store all the data that you have. So whenever you make like a query and you say, what about this point? It has to be like, OK, who's the 20 nearest neighbors? Blah, 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 and spits back out. And the best way to select a k is you just choose a whole bunch of different k's and you cross-validate and see where you're getting the best predictions. So that can be kind of expensive and kind of a pain to do. Now, another thing that this is more historical note is another possible algorithmic modeling tool is called the perceptron algorithm. And this assumes that there's only two classes and that they're perfectly linearly separable, which means that I can find a line that perfectly separates them, so I haven't misclassified any single point, right? And extensions exist for this when k is greater than 2. But so when I say for k equals 2 classes, I'm just saying for our particular example. So if I let y be like -1 and 1, and I define some sort of linear separator of this form, then I'm going to say, the way this line works, that if my response is actually 1, but my classifier predicts some value less than 1 or less than 0, then I've misclassified this point. And if y is -1 and my linear separator predicts greater than or equal to 0, then I've also misclassified this point. So I'm trying to minimize my misclassification here. So it's really what you're doing. Video's not going to get this, but you've got some sort of like points like this, and you start off with some guess here as some sort of classifier, and then you jiggle it around until you finally get one where you've got 0 possible misclassification. That's really all this is doing, and this is why it's historically really, really a simplistic idea, but it led to some really good results. And so again, the idea is you minimize this particular function here, And Frank Rosenblatt is the guy who created this, and he showed that this solution is guaranteed to converge in a finite number of steps if it's linearly separable. But it does not say what the number is on those number of steps. Finite is great, but if it's 5 million, you might have a bit of a problem. So some pros and cons of this. Perceptron is a really cool word because it sounds like some sort of 1950s sci-fi villain. And it's also amenable to online learning because the data are processed one at a time. So if you have a lot of possible data points, you can just feed it in and it makes the adjustments as is. It doesn't need to take it all at once like what you have with k-nearest neighbors. But the problem is it might converge really, really slowly. The solution you get is not unique. I could have drawn a slightly different line here and that would perfectly classify points, so that's not super satisfying. And if it's not linearly separable, it'll just keep going for a long time, but you don't know, maybe it's converging to the right thing or not. And really the biggest issue with this whole thing is that perfect linear separability is a massively huge assumption, right? That's rarely ever going to be satisfied, that you don't have any overlap between points. But still, they did some really cool stuff with this. So this is Frank Rosenblatt with this what he called the perceptron. And they would be able to hold shapes up to it, like a triangle or a circle or whatever, and it would be able to, it had all these different sensors on here, and it was basically running the perceptron algorithm, and then it would predict, oh my God, it's a triangle, right? And so now it's not this tiny little thing. These are wires connected to it, and it's like a whole room thing, right? So these are just the photo sensors. So this whole thing is really cool, but I thought that was a cool little picture. And there was a New York Times article on the perceptron algorithm. Now notice it's a very, very simplistic algorithm. And they said, so this was research that was funded by the Navy. The Navy revealed that the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Later, perceptrons will be able to recognize people and call out their names and instantly translate speech in one language to speech and writing in another language. It was predicted. So there was all this hype. And that's not just the news media overhyping it a little bit. Like Rosenblatt was known to be a very eccentric character. And so it turned people in the scientific community a little bit off to it because they were selling it like it was this, the end-all, be-all of classification and artificial intelligence. The problem was Minsky and Papert in 1969 in their book called Perceptrons showed that this classification could be a simple exclusive OR function. So I'm going to go back over here. So all that's saying is if you had points like this, where you've got a circle, an X, and an X, you're not going to be able to find a linear classifier that's separate. You've got 4 points there, and it's basically the simplistic model in the world. But your perceptron breaks down. It's not going to be able to possibly get that. So this is a really simple function. So, I mean, how are you going to walk, talk, and reproduce if you can't even figure out, some way to classify those separately? So it really made a huge impact on the field negatively. In fact, that people kind of jumped out of the perceptron world. And that's sad because Rosenblatt, so he was super excited about this. He ended up dying in a boating accident in 1972 and not being able to see that. Just the next decade, somebody came out and like, oh no, but if we make this minor tweak and make multi-layered perceptrons, we're okay, and it can totally handle stuff like that. And so it came back with a vengeance, and like any good comeback story, it was rebranded as artificial neural networks. So you guys have heard of artificial neural networks. It's just the perceptron with multiple layers. And I was going to go into detail on this, but there's so much on artificial neural networks that this should really be another topic that we talk about. But each of these things is acting as a perceptron, and when they all work together, they achieve great things. So it's a really good story. And this also forms the basis of deep learning, which is something that has been really, really big in the artificial intelligence world lately. It's what's been winning all the Kaggle competitions and classifying galaxies and stuff like that. So deep learning is the buzzword, but really at its core, it's just artificial neural networks. Another thing, so this is one of the last major topics I'm talking about, is decision trees. Now decision trees are awesome because what decision trees do is it's a very, very intuitive way of classifying observations. You look at the available data and you do some sort of recursive binary splitting. So what you do is you look at your data, you look at all your different variables, and you're like, which variable separates the data the best? Now, I don't care if that data or if that variable is categorical or it's quantitative or what. I'm just trying to split the data into two different groups so that the classes within this group are mostly the same and the classes within this group are mostly the same. That's really all you're trying to do. So it's recursive because you just keep repeating that step, and it's binary because you're only making two splits at a time. Now, they call it decision trees because it breaks off and it starts to look like a tree. And like any good method, everyone took the tree analogy way too far. And so you've got all these different terms in the decision tree world called root, which is where you start. And then branch is when you keep splitting it off, so the different splits are branches. A leaf is a terminal node, so then you're just going to say, classify all those points as there and it doesn't have any more branches coming off of it. And this is my favorite one. Pruning is after you create the entire tree, you remove the least beneficial branches and leaves, the ones that are not giving you the best classifications, just so you've got a more simplistic model. You reduce the complexity, you prevent overfitting. There also, I read stump was if you just got two of them, so people are taking it way too far. But it makes it easy to remember. So there's different ways that you can make the split. You can do a misclassification rate where you're just going to say, I want to minimize the misclassification between these two groups. But that's typically not used. Typically what we want to use is something called the Gini index or the cross entropy or deviance. And the reason that is because here's an example. If you've got k equals 2, I want to minimize this at any split. So I would prefer to be over here or be over here because that means that my proportion of me classifying, like when I classify two different things, I'm mostly classifying them correctly, if that makes sense. And the Gini index and entropy are smooth continuous functions, so they're differentiable. A misclassification error is not. So when y'all want to minimize it, it becomes really, really easy. So again, you could read up on that quite a bit more than I have. So I did a quick example. I found this really cool data set on different mushroom species and whether or not eventually I want to predict if they're edible or poisonous. And they have a whole bunch of different variables like what the cap shape, the cap surface, color, does it have bruises or not? What does it smell like? Tell me about the gills, and then a few different other, what is the stalk, is it short, is it thick? Just a whole bunch of different possible variables, and you want to predict, can I eat this mushroom and not die? So I do decision trees on it, and I figure I might take the tree pun a little too far, so I call my decision tree related to fungi data, I call it the mushroom. And if I summarize the mushroom, you can use the tree library and do the classification. And so really all it does is it picks out, okay, the only variables that it thought were the best were odor, the spore color, like what falls off of it, the stalk color below the outer ring, and the root, what the root looks like. And when you run through this, the data set's like 8,124. You only misclassify 8 of them after this, only based on these variables. So the decision tree was able to pick out exactly which ones are the most useful. And here's a little bit more output that tells you what your classification is along the way and how you're making your splits. So for odor, A, L, and N correspond to different odors that they have, and you would put that in one group versus another group. So visually, it's a little bit more easier to tell. You look at odor, and if it falls into any of those categories, you move over here. If not, you're going to say that it's poisonous. But if you move over here, let me look at spore print color. If it's any one of these, I keep going. If it's not, I'm going to say that it's poisonous. You move down here, oh, it's edible. It's not, let me check, edible, poisonous, right? So it's really easy, and probably the best thing about these decision trees is that they're intuitive. And I was going to put interpretable, but I felt like I should just be able to say super interpretable, because you could give this to like any consulting student. I could give it to my 311 students, they would know what's going on. So that's amazing. They're just really easy. I mean, they're they're glorified flow charts. And it can handle both quantitative and qualitative variables, and you don't need to do any sort of data pre-processing. You don't need to create dummy variables for your categorical stuff. You just toss it in, and your trees happen, and it's awesome. But it doesn't count for dependence between variables within each class. And the problem is there's high variance between trees. So if you've got a data set and a different data set, if you create a tree on this one, and like just from if you get a data set and you create training sets and then test sets, your tree might vary a lot between this training set and this training set and this training set, which is kind of annoying because then which one is right, you know? I mean, which one do you use? And so people have addressed this with what they call ensemble methods, which is you grow a whole bunch of different trees and then you kind of collectively average them, or you account for them in some way. And so it's intended to lower the variance. So by looking at a whole bunch of different single trees and collectively looking at them, I don't have as much high variance from just looking at one tree to one tree from one tree. And the issue is, though, that you miss that really nice interpretability. You're not able to like have this nice, like, oh, if I'm here, I go here, I'm here, I go here, because you've got a whole bunch of different trees and then you're weighting them differently. So you lose some interpretability, but it's really supposed to improve prediction. So again, if you're looking for something to give to a client, maybe one decision tree is the way to go. But if you're looking for just straight up prediction, you should probably be using some sort of ensemble methods. So one way to do that is what's called bagging, and it's just it just stands for bootstrap aggregating. And all you do is you take B bootstrap samples from your data, you grow trees, you don't do any pruning on the trees, you let them grow, and then for each of the samples, and then for any new observations, you just look at across your B decision trees, majority vote on what that observation got classified as. So I've got B possible trees. If most of those are classifying it as group 2 versus group 3, group 4, then that's how I would do it. And then the problem, though, is that if you've got a really good variable that splits it, all the trees are going to, and that happens to be, that's probably going to crop up a lot in every single decision tree you make for every single bootstrap sample. So if you, for that one that we saw, odor seemed like it was the biggest splitter. The problem is if you did bootstrap samples, almost every single tree that you have would have the big odor split at the beginning. So you don't really, you've got high correlation among your trees and you're not really diversifying your tree assets very much. So one way to alleviate that is what's called random forests. And all they do, the only modification they make there is instead of using all the predictors, all P predictors, I'm going to take a random subset, that's what the random stands for, random subset of the P predictors. I'll call it M, which is approximately square root of P. You know, you can choose what is most appropriate for your problem. And then do exactly as you did before with the bagging. But so that way, you're going to get trees in this case where odor is not the best splitter, and you might have other variables that help out. But again, this has been shown to really, really improve prediction. So most people are using random forests. There's another thing called boosting, which is a little easier to do in regression decision trees versus classification decision trees. So I didn't talk about it here. But if you see boosting or random forests, this is all they're doing. They're just building a whole bunch of decision trees. So yeah, decision trees are awesome. Support vector machines, I'm not going to steal Jamie's thunder by any means. But I can't have a supervised classification talk without mentioning support vector machines. So all I'm going to say is that they became very popular, particularly in the 1990s, and they're still popular today. And that's another big supervised classification technique. But again, if you want to learn more about them, Jamie's talk is on November 7th, I believe. And she'll be talking about support vector machines then. So in summary, if this, oh, there we go. So there's no shortage of supervised classification methods. There's a bunch out there. I had to whittle down my list of possible methods to talk about because there's just so many. But before you do any modeling, you should make an important choice. Do I want to do data modeling or do I want to do algorithmic modeling? If you're looking for straight up predictions, algorithmic modeling seems to be the way to go. But if you're really looking for variable selection or any sort of inference on your parameters, then you might be looking more at a data modeling context. And sometimes the best option, I mean, it sounds crazy, but it's just don't make a hard choice to just run a whole bunch of them and see how you're doing. To run cross-validation using logistic regression, LDA, maybe k-niche neighbors and something else, if computation is not prohibitive, and see which one's doing the best. That seems to be a lot of times what people do. And I found this quote. So no matter what model you get at the end of the day, it's all subjective depending on what method you use. So you're only as good as what you want to use your data for. So I found this quote: "The great masters do not take any model quite so seriously as the rest of us. They know that it is, after all, only a model and possibly replaceable." So don't get wedded to your model like it's the best thing in the world. Again, it's a tool that you're using to learn something about your data, and that's it. So yeah, be careful. Anyway, That's it.